One of the questions that arose in our studies was what happens if you have a degenerate system, namely one in which the linearized matrix has a 0 eigenvalue. Well, there are several kinds of degenerate systems, but let us look at a specific example, the simplest of these. So let us look at one for which x dot is perhaps ax plus by and y dot equal to some constant times the same thing, ax plus by. So of course this immediately implies that L is A, B, K, B. So delta equal to determinant L is identically equal to 0. Then the question is what kind of critical points you get here, and the answer is very simple. You have a degenerate system, these two equations are not linearly independent of each other, this is just a multiple of that, and therefore in the xy plane if you plot the locus of the points on which the right hand sides are 0, you get ax plus by equal to 0 or x or y equal to minus a over b x, which perhaps is some straight line of this kind, and at every point on this line, critical line if you like, the system is in equilibrium, no time change at all. And then of course you could ask what is the flow like, what happens if you have an initial condition which perhaps starts here. This would depend on what the signs of these constants are, but in general the flow would be either along this line inwards everywhere into this line, or perhaps outwards, all the arrows going outwards. So this is a very simple example of a degenerate system, it is not of particular interest to us right now. More serious would be what happens if the system is not linearizable intrinsically. The example that we look at is even in a 1 degree of freedom system, for example, just a single variable, if you had something like x dot equal to x squared and you ask what does this do, what kind of critical points do you have in this situation. Well, we have a phase line, there is a critical point at 0 and we can't tell whether it is stable or unstable in the conventional sense, because for positive x the flow is outwards, but for negative x also x squared is positive and therefore the flow is inwards in this direction. Therefore this is, as far as the left hand side is concerned it is an attractor, but as far as the right hand side is concerned it is a repeller, it is a higher order critical point. Now the question is, can we say something else about it, and how does this higher order critical point arrive? Well, it occurs because x squared is not a generic polynomial on the right hand side. If I ask you to write down a polynomial on the right hand side or something which is expandable in powers of x about the origin, you would start by writing a0 plus a1x plus a2x squared and so on and so forth, and unless you have a special accident so that a0 and a1 are both 0, you never start with the x squared term. On the other hand, if I put a constant here, just a single constant, you can always absorb that constant by shifting x to that point. So the constant is irrelevant, but certainly the linear term is missing. So the sensible way to do this would be to ask, instead of looking at this system directly, unfold this second order 0 if you like, this double 0, by writing this as equal to some epsilon x plus x squared, and examine what happens for various kinds of epsilon, small positive, small negative or 0 epsilon. Epsilon equal to 0 corresponds to the case you have, but epsilon positive or negative would be a generic system and you could linearize it in the origin of these points. Well, in this instance for example there is a critical point at the origin and there is also one at minus epsilon. So there is one at minus epsilon out here in the instance in which epsilon is positive, then of course minus epsilon is located here, and you could ask what kind of flow do you have. Once again near the origin here in the vicinity of the origin, I could write x dot is approximately equal to epsilon x, which means if epsilon is positive the flow is outwards along the direction and outwards along this direction here. By continuity therefore it remains in this direction all the way up to this critical point, and now you ask what kind of critical point is this. For that you have to linearize about this point. So the sensible thing to do is to put in this neighborhood is to put u equal to x plus epsilon, so that the origin in u is the point x equal to minus epsilon, and then ask what happens to this system. Well, that system now becomes u dot equal to u multiplied by x, because this is x plus epsilon times x, but x is u minus epsilon, which is equal to minus epsilon u plus u squared. Once again, if you linearize in the neighborhood of this point, then the linearized equation is linearized, its u dot is approximately equal to minus epsilon u, and since epsilon is taken to be positive, it is flowing into this attracting fixed point here, and it is flowing in this way, the other direction. So you have an attractor at minus epsilon and a repeller at the origin, and the coalescence of these two when epsilon is 0 produces for you this figure, this higher order critical point. And this picture is valid for epsilon greater than 0. This picture therefore corresponds to epsilon equal to 0, and one could ask what happens if I had chosen epsilon to be negative to start with. That is easily taken care of, because if epsilon is negative, the fixed points are at the critical points are at 0 once again, and at the point minus epsilon, which is now on the positive side since epsilon is negative, and it is easy to see that linearization about the origin is always x dot is epsilon x, and since epsilon is now negative, the flow is inwards into the origin on both sides in its neighborhood, and it is a trivial matter to check once again that the flow is outwards from this point at the point u equal to 0 or x equal to minus epsilon, because epsilon is negative, this number becomes positive here, minus epsilon, and it is a repeller. So what happens effectively is that this point becomes a repeller and this becomes an attractor. So now we get a much better picture. It says that the system x dot is x equal to x squared, which is intrinsically nonlinear, really arises by an accident. It arises by the coalescence of two critical points, one at the origin and one at minus epsilon, as the second critical point minus epsilon crosses 0. As it crosses the origin, as it crosses the value 0, you get what was initially, to start with, starting with positive values of epsilon, an attractor at minus epsilon and a repeller at the origin, becomes a higher order critical point when the two of them coincide, and then as you move over to negative values of epsilon, you have a repeller at minus epsilon and an attractor at the origin. So there has been an exchange of stability, and this is called an exchange of stability bifurcation. It is an honest bifurcation, one of the simplest one can think of, and we draw what is called a bifurcation diagram, in which I would plot as a function of the parameter epsilon, I would plot the equilibrium or stationary value or steady value of x, in this case the value at the critical point. But there are two critical points, one of them is always at the origin, and therefore you have a line on this axis, and the other one is at the point, is at the value minus epsilon, and that is a straight line which is tilted at 45 degrees and of this kind, and this, if you like, is x equilibrium. On the other hand, I know that for negative values of epsilon, this critical point is unstable, and therefore I denote that in standard notation by a dotted line. So I write this as a dotted line here. For negative values of epsilon, it is unstable, and therefore I have a dotted line of this kind, and a solid line here to indicate that this is a stable critical point. So this is unstable, and this fixed point is stable. When you cross over to positive values of epsilon, what was stable becomes unstable, in this fashion, and what was unstable continues on as stable. So this is stable and this is unstable. And we have an example of a bifurcation, which in this case is called an exchange of stability bifurcation. We would like to now ask a slightly more general question. What kind of bifurcations can we expect in such systems? This was a simple one dimensional system, but it can be generalized to higher dimensions, and the question is, what kind of elementary bifurcations or distinct kinds of bifurcations do we have? This problem too has been analyzed in great detail, and bifurcations have been classified, at least the elementary ones have been classified in simple dynamical systems. I should mention that bifurcations which involve a single parameter which you tune, in this case just epsilon, they are called bifurcations of codimension 1, and this is distinct, this dimensionality is distinct from the actual dimensionality of the phase space that we are dealing with. This is in the parameter space and there is just a single parameter here, so it is a bifurcation of codimension 1 in this instance. We will see later that we have bifurcations of higher codimensions, and classifying them is a non-trivial task. Classifying bifurcations in general in higher dimensional dynamical systems is a fairly non-trivial task. Now I would like to put this in the framework of a slightly more general setting, and that is as follows. So I would like to look at it as two dimensional phase space, but just to get a physical feel for what is meant by tuning this epsilon, let us cast it in the language of a mechanical example. So what I intend to do is to consider a particle of unit mass moving along the x direction and look at these dynamical equations as equations of motion for this particle in some potential v of x. So the equations of motion are x dot equal to p, if I consider unit mass, this is the momentum here, and p dot equal to minus dv over dx, which is the force on the particle, and I am going to tune this by writing different kinds of functional forms for this v of x and asking if I can examine bifurcations in this framework here. Now what would you say is the simplest of these forms that we could write down here? Typically I would write down various kinds of polynomials for this force here, and the simplest of these that one could write down is perhaps to say that this is a constant plus a linear term in x, but it is quite clear that if you have an a plus bx here, the only critical point is at p equal to 0 and x equal to minus a over b, and that is it. There is just a single critical point and there is no possibility of any bifurcation, no coalescence of singularities. The next non-trivial case would correspond to putting in here some parameter, and let us various symbols could be used. Let us use a and let us put a bx squared here in this case. Okay. What kind of potential does this involve? What is the shape of v of x in this case? If I plot here x versus v of x, remember this is the force, it is minus dv over dx, so this would imply that v of x itself equal to minus ax plus bx cubed over 3 minus x cubed over 3. If I integrate this and change the sign, I end up with this. Okay. What kind of shape is that? It is a cubic curve, and clearly we would like to plot it, and we should like to know whether a is positive or negative or what. Let us fix the sign of b, let us take b to be positive for example. You could simply redo the whole thing for b negative, there will be no essential change in what I am about to say. So let us suppose that b is always greater than 0 and a could be negative or 0 or positive. Let us look at all possible cases. Now what happens if a is negative? What is the shape of this curve? So I plot this for a negative, and the shape of this graph is approximately linear at the origin with a positive slope. and therefore the potential looks like this here, but eventually this term takes over and that is a large negative term, so it is evident that this is going to go down and fall down. On the other hand, when x is large negative, this term dominates and becomes positive in sign, and therefore the potential has a shape of this kind. So one knows immediately that the critical points of the system occur at p equal to 0 and this quantity equal to 0, and what does that look like? What would this do? Well, it is clear that there is an equilibrium point here at this point, and that is a saddle point because it is a maximum of the potential, and this point here is a minimum of the potential, and therefore this point is a center. Since there is no friction in this problem, you would have small oscillations about that point, about the minimum of the potential, whereas the maximum of a potential in the absence of any dissipation is always a saddle point, and this is all that a Hamiltonian system could have. We have here a Hamiltonian system in which the Hamiltonian is p squared over 2 for unit mass plus v of x, and these are Hamilton's equations that I have written down, and this is the picture that we have. So we clearly have critical points at p equal to 0, and the values here correspond to x equal to minus a over b square root of this with a plus or minus, and this is the picture for a less than 0. Remember, the plus corresponds to the minus, this point here corresponds to a center, and the plus corresponds to a saddle. You can write down the 2 by 2 linearized matrix and check out at each point that this would correspond, this center would correspond to a pure imaginary pair of eigenvalues, and this would correspond to one positive and one negative eigenvalue if you linearize about these values of x. We know how to do that now. What happens if a is exactly equal to 0? Once again, if I plot at a equal to 0, I plot the potential v of x versus x. What would this correspond to? This term is gone and you just have a minus bx cubed, and that at the origin is extremely flat, it has an inflection point and it falls off in this fashion, again for b positive. So this point here has arisen because this maximum and this minimum of the potential have come together at the origin, and it has become an inflection point where the slope is 0 and the second derivative, the curvature, is also 0 at this point. And now finally, what happens when a is bigger than 0? So we look at the picture a greater than 0, that is the third case, and if I plot x versus v of x, then when a is positive you have a negative slope here, and therefore this curve looks like this, approximately linear, and then of course as x becomes larger it falls off like a cube and it increases here like a cube. There is no possibility of any equilibrium point at all in this potential, there are no maxima or minima at all. There are no critical points in this dynamical system because if a and b both have the same sign, there is no way this quantity can vanish. So that immediately tells us that you do not have any critical points in that system, you have a degenerate critical point in this system, and you have here two critical points which have separated out. And therefore if I now plot the equilibrium values, let us plot x equilibrium here versus a parameter, and the parameter in which you have this variation is in fact a, To plot this I need one more direction, I need P as well coming out of the plane of the board, but since P is always 0 at the critical point, I ignore this P, it is always 0, so let us just plot it in a 2-dimensional diagram here, x equilibrium versus A. And what is the picture one has? For A positive, nothing. For A negative, you end up with a saddle point at x equal to plus square root of minus A over B, and a center which is stable at minus the same value, and this is changing or increasing in magnitude like the square root of minus A, therefore it is a parabola which goes up in this fashion and falls down in this fashion. However, we know that this root here, which corresponds to plus square root of minus B over A, is unstable, and this is stable. So this branch which is minus square root of minus A over B is stable, this branch here which corresponds to plus square root of minus A over B is unstable. We could have had this parabola looking the other way had I put a plus Ax here, then the role of minus A and A plus A would just get interchanged, but what is happening here clearly is that if you imagine changing A in parameter space from positive values to negative values, no critical points at all in this region, and all of a sudden at this point a pair of critical points gets created, and what is happening is that if you start with this potential and start flattening it out, then at the value A equal to 0 you have a cubic, you have a second order 0 here, you have an inflection point here x cubed, and then below that the inflection point unfolds into a maximum and a minimum, and you have this shape here, and of course you go on changing A, making it more and more negative, these points will move out further exactly like a square root of minus A, and this is what happens here. This bifurcation where out of nowhere a stable and an unstable critical point emerge and move off is called a saddle node bifurcation. In this case at the value A equal to 0. You see immediately that this is different from the bifurcation we looked at, the exchange of stability bifurcation, altogether different. So a saddle node bifurcation is one where as you go across a critical value of the bifurcation parameter, a pair of critical points is created, typically one of which is stable and the other is unstable. So much for this simple form. We could make this a little more complicated, let us do that. And the next step is to take this potential and ask what happens if it is Ax plus Bx squared. This would correspond of course to V of x equal to, incidentally the signs of these quantities A and B, I have taken them to be arbitrary here, it does not matter which way these bifurcation diagrams look, the physics is essentially the same thing in all cases. Now what happens to the potential? It is minus Ax squared over 2 minus Bx cubed over 3 if I integrate this function out. Once again we can predict what is going to happen. We start again with A less than 0, A equal to 0, and finally A greater than 0, and plot in all cases the potential V of x as a function of x. Out here for A negative, minus Ax squared over 2 is an upward looking parabola because it dominates for sufficiently small x, and therefore this curve is going to look like this, but then once x becomes sufficiently large, this negative term is going to dominate and bring this potential down in this fashion. On the negative side, this always remains negative, and for x negative this number is also positive. So what happens there? He seemed to have made a mistake here. So let's keep b positive here. This term is going to dominate, so it's positive. Yeah, there's no problem. This term becomes positive. Yeah, so that's fine. This goes up here, because eventually for large negative x, this term dominates over this. Minus x cubed is negative and minus x cubed is positive, so it goes up in this fashion. So this is fine. Okay, yeah, this is fine. When a is 0, exactly 0, then it's just a cubic curve, exactly as I drew earlier, minus x cubed, which has an inflection point here and goes down in this fashion. And for a positive, you have a downward parabola here, and of course for large negative positive x, this is going to become a large negative quantity, go down there, but then it has to eventually turn back and go off in this fashion. Now it's easy to see what's going to happen. At a equal to 0, you have a higher order critical point here. For a negative, you have a maximum of the potential which corresponds to a saddle point, you have a minimum which corresponds to a center at the origin. On the other hand, for a positive, the origin corresponds to a saddle point and the minimum which occurs here corresponds to a center. So what has happened? What kind of bifurcation is this? And where is this point? This point, mind you, is not at x equal to 0, but it is equal to at minus a over b. This point also is at minus a over b. It is as if the diagram has moved, but what has happened is that the critical point at p equal to 0 and x equal to 0, which was initially a center, has now become a saddle, and the critical point at p equal to 0 and x equal to minus a over b, which was a saddle point, has collided with the center at the origin and has now become a center. They have therefore exchanged roles. Now what is this bifurcation? This is an exchange of stability bifurcation. So it is evident immediately in the bifurcation diagram. If I plot, the parameter is a, if I plot this versus x equilibrium, as long as a is negative, this center at the origin is stable. So we have this picture, this is stable, and once a becomes positive, that point becomes unstable, and therefore you have a dotted line here on the a axis. But the critical point at minus a over b, this thing here, which is just a straight line with slope minus 1 over b, and we have taken b to be positive, something of this kind is unstable there and is stable at this point. That is the location of this critical point, and for a negative it was clearly unstable, and for a positive it is a center and is therefore stable, and we have an exchange of stability bifurcation. At a equal to 0. This bifurcation has another name, it is also called exchange of stability or transcritical. A bifurcation. The saddle node bifurcation, incidentally, is also called a tangent bifurcation. This is a matter of terminology, but there are these alternative names. We have looked at two distinct bifurcations, and one could go on and ask, are there any other bifurcations of codimension 1 because the critical parameter here is A, the one that you are tuning. Well, the next step would be the following. One could play this game, one could continue. The next step would be to say, what if the shape of the force or the potential, corresponding potential, what if this was ax squared and this was bx cubed, this fashion? What then? This would of course imply that the potential V of x, let us make this a little stable so it looks physical. Let me make this minus, make this also a minus sign. We will see in a minute why, because I want to draw convenient pictures in this case. V of x then becomes equal to ax squared over 2 plus bx4 over 4. So the three cases that we have looked at were constant and quadratic function x squared. Then we had the next situation was an x and an x squared. And the next case I am looking at is an x and an x cubed here. The potential corresponds to minus the integral of this function, the primitive of this function, which is ax squared over 2 plus bx4 over 4. If I differentiate it and take a minus sign, I get precisely this. What kind of picture do I have now, and what would you expect? Once again, the simplest way to do this is to plot the potential as a function of x. We plot V of x in all three cases. So V of x versus x, and let us do the same thing, V of x versus x for respectively a less than 0, a equal to 0 and a greater than 0. I am actually going the other way, but it does not matter, a equal to 0. It is easiest to plot this potential because it is always positive. We have taken B to be positive always, in which case for sufficiently large x this is going to dominate, and that is just an x4 curve moving up steeply, and near the origin this is a parabola turned upwards, concave upwards for a positive, and then after that it increases more sharply, so it is parabolic at this point and increases very sharply this fashion. So one immediately knows what the critical points are. There at the origin there is only one critical point, and that is at p equal to 0 as well as x equal to 0, and it must be a center because this is a minimum of a potential. At a equal to 0 this term is absent, and you have a very flat potential at that point. Not only is the derivative 0, but the second derivative is also 0, as is the third derivative. It is a minimum, but it is not a simple minimum, because you can see it goes like this point, bx cubed equal to 0 at this point. And what happens here? When a is negative, for small x this term dominates, and since a is negative, it is an inverted parabola, so it is a curve like this, but eventually the x4 term will dominate and take over, and you have a symmetric graph of this kind. Unlike these cases where you just had a minimum at the origin, now you have a maximum at the origin, but you have two minima at these points. And what are these points? These points are given by the vanishing of this quantity other than x equal to 0, and those roots are at x squared equal to minus a over b, therefore x equal to plus square root of minus a over b, and this is at minus square root of minus a over b. Those are the locations of these points, and it is evident that these are centers, and this point is a saddle point in between. We can therefore draw a bifurcation diagram now without further ado, and this as a function of a, I plot x equilibrium, and what does it look like? For a positive there is just a single critical point at p equal to 0, x equal to 0, and here since p is always 0 we have not drawn it. So x equilibrium is 0 and it is this line, and it is stable. So this fixed point, this critical point is stable. When a becomes negative, that critical point becomes unstable. So we have to replace this with a dotted line on the other side, and this is unstable. However, two new critical points emerge and move away from the origin, and they are at plus or minus square root of minus a over b. So as a function of a they go like square root of minus a, which would correspond to a parabolic shape there and a parabolic shape here, and this is stable, this is unstable, this is also stable, sorry, this is also stable with an unstable critical point in the middle. And that is obvious because you can't have two minima of the potential without a maximum in between. So automatically you realize that stable and unstable critical points would tend to alternate. Now what does this figure remind you of? It is a different kind of bifurcation altogether from either the saddle node or the exchange of stability bifurcations. Here we have a stable critical point coming along and bifurcating, continuing as an unstable one, and a pair of stable ones is born. What does this figure remind you of? It is a combination of both in some sense, but this figure, because it resembles a pitchfork, is called a pitchfork bifurcation. A saddle node bifurcation or a tangent bifurcation had no critical point at all, and then the creation of a stable unstable pair. An exchange of stability bifurcation was when a stable and unstable one collided and exchanged stabilities, and a pitchfork bifurcation is when a stable bifurcation bifurcates into a pair of stable ones and an unstable one in the middle. Well, one could go on and ask, suppose I go on increasing the powers here, what would happen? While it is true that you could in principle get what looks like new kinds of bifurcations, the fact is these are the only three generic elementary bifurcations of codimension 1 in such systems, in continuous time systems. So the three elementary bifurcations of codimension they are A, the saddle node, or tangent, B, the transcritical or exchange of stability bifurcation, and C, the pitchfork. We have illustrated these bifurcations in the framework of a simple mechanical system, drawing pictures using these potentials, but as we saw right in the beginning when I gave the example of the transcritical bifurcation, they could occur in dissipative systems as well. So there is nothing which says these are exclusively restricted to Hamiltonian systems or potential problems or anything like that. It is the phenomenon that is important, and this is what basically happens. These are elementary because you could have more complicated coalescences of bifurcations. So in exactly the same way as saying for instance the elementary functions which I would have of a variable x expandable in power series would be 1 x, x squared, x cubed, and so on, and from these I can construct polynomials, I can construct more complicated combinations. In exactly the same way, in some sense, these are the basic things that happen. Pardon me? No, the pitchfork is not a combination of the others. No, it is not. It is a very different shape altogether. You can see from the potential example that I gave, this is a very different thing altogether here. If you go back to the potential example, you had a cubic potential and that cubic curve could have a minimum and a maximum. It need not, a general cubic curve need not have a cubic and a specific cubic curve need not have a minimum and a maximum, but it could depending on what the parameters are, and that is exactly what led to the saddle node bifurcation. Similarly, if you took a cubic curve, then the position of the minimum and maximum could get exchanged. This is what led to the exchange of stability bifurcation. A fourth order curve of this kind could have 3 extrema, but it could also have one, just one right here, and as it transits from the situation where it has one extremum to where it has 3, which is the largest number it can have, you end up with a pitchfork bifurcation. So clearly what has happened is, depending on what kind of polynomial you have, what kind of unfolding of these singularities you have different kinds of bifurcations. And of course one could ask, what would happen if I did not have an x cubed here and an x here, but I had an x cubed here and an x to the 5 here, for example, etc. Those would not be the most elementary ones, they would be more complicated versions of what we already have. So these are the only 3 elementary bifurcations for continuous time systems. As I said earlier, the number of bifurcations possible, the classes of bifurcations possible in general dynamical systems is not known in general, especially if the codimension increases beyond 2 or 3 or 4, then it is hard to classify these bifurcations, although a lot of work has been done in this along these lines. But for the elementary cases we are looking at, these are the basic ones, the bifurcations. We will come across a few more, we are going to study in this course a few more bifurcations which are also elementary bifurcations, but which are not of these types, and they occur in slightly different dynamical systems, as we will see. There is one more which is very, very important, goes along with these, and that is called a Hopf bifurcation, and to lead to that I need to introduce yet another concept, namely that of a limit cycle. So let me do that now. Yeah.
One more thing was, you talked of y is equal to x square.
Yes.
That sort of a degeneracy.
Yes.
So that could be approached by either a plus bx square or ax plus bx square, right? Is there any case by which like
okay. Oh yes. The question is, what is the correct way of unfolding a given degenerate form? And there is an elaborate mathematical machinery to do this. All these bifurcations are cast in what is called the normal form, namely the minimal form or the minimal expression which leads to that phenomenon, the bifurcation. These are already, the ones I have written down here are already the normal forms, apart from some constant multiples or scaled, which could be scaled out, some constant factors. These are already the minimal forms. You could make them a little more complex. There is a branch of mathematics called catastrophe theory which deals with this problem of unfolding these singularities and writing things in their normal form, the minimal form, and this is there is an elaborate theory to this effect, and I have just given a flavor of it, a little glimpse of it in writing these forms down. So there is a systematic way of doing this, of unfolding these singularities. And let me go on now to the idea of a limit cycle, and let me introduce this as follows. In our study of two-dimensional systems, we looked at various kinds of critical points. These are points where the right hand sides of the two dynamical equations vanished. One could ask, are there sets of points, continuous sets of points where you have some kind of equilibrium? So you do not have point attractors or point repellers, point singularities in the vector field on the right hand side, but can you have lines, or can you have whole sets of continuous sets of points where you could have such behavior, equilibrium, kind of equilibrium behavior? But the answer is yes, because let me do this again with the help of examples, and then these are called limit cycles. We are going to say a lot more about limit cycles as we go along, because this is a typical feature of nonlinear systems, and unlike the case of critical points, these are much harder to detect and study, so it makes them interesting. And let us look once again at an example.